So continuing in our discussion of the definite integral as opposed to indefinite integral. So definite integrals are integrals that have a lower and an upper bound, or a lower limit and upper limit of integration. So what we know, what we're going to learn to understand, is that an integral represents the area under a curve. So if the function is non-negative, meaning it's above the x-axis, and we can find the integral on some closed interval, then the area under that curve, f of x, along that interval, a to b, using a and b as my lower and upper bounds, is the integral. So what this definition says is the integral represents the area under the curve between an initial point A and a terminal point B, some horizontal interval. We can find the area. What is important is that it is non-negative, right? So that means the function has to be above the x-axis. So if we had some function that went like this, and say we wanted to find the area maybe from A to B. Now, that part of the curve is below the x-axis. And with it being below the x-axis, what that means to us is that the area would actually be a negative value. And so we'll get more practice with that later. But, you know, I do think the fact that we say a non-negative function. So let's do an example. And before we get into the integral process of it, let's just think about, you know, regular shapes, finding the area under the curve of something that's creating a regular shape, like a circle or a triangle. And in this situation, we would say, let's find the integral from -3 to 3 of the square root of 9 minus x squared dx. And so what does that represent? If we think about that as being my function, right? The square root of 9 minus x squared. Well, that's like, y is the square root of 9 minus x squared, or y squared equals 9 minus x squared, or rather x squared plus y squared equals 9. So this function represents a circle, albeit the top half of a circle because it's positive, the square root, but that's a circle of radius 3. And if you pulled out your TI calculator and plugged that into your y equals value, you would see a shape that looks like this, the semicircle, a top half of a circle. And we would have this endpoint -3, 0, and the right endpoint +3, 0. So this is the area of a circle, and the area of a circle we know as a regular formula is pi r squared. So the area of half a circle, right, the area of some semicircular region, that half of a circle, is pi r squared divided by 2. So this is a circle of radius 3. The area of the circle would be pi times 9. Therefore, the area of the semicircle, this integral here, what the answer would represent would be 9 pi over 2, because I'm plugging that radius 3 in here. Pi times 3 squared over 2. And so that 9 pi over 2 represents the area of this shaded semicircle. One thing to notice is that everything we were calculating the area of in this situation was above the x-axis. So let's do another example. Here we're given a problem. Find the area, we'll call that A, under the curve y equals x over the interval from 0 to b, noting that b is a positive number. Okay, so what that means, or how we translate that, you know, and saying y equals x, that's the same as writing f of x equals x. So x is going to be our integrand. So my area is going to be equal to the integral from 0 to b, and I'm using 0 to b because that is my interval of my function. In this case, my function is just x, and we are integrating with respect to that variable d of x. So as we think about solving this problem, let's think, what might this graph look like? So I'm going to come over here and draw this. So the graph of the function y equals x, or the identity, is a perfect diagonal line coming through the origin at a 45-degree angle. And we are looking at the integral from 0 to, say, some endpoint b. So my region of interest here is this 45-degree right isosceles triangle. It's this region. So if I were to calculate my indefinite integral of x dx, which we learned about previously at the beginning of this section, that would be x squared over 2 plus c, plus some arbitrary constant c. So what this means for us using our definite integral notation is this becomes x squared over 2, and we can put a bracket or just a line, evaluated from b to 0. So when we're solving a definite integral, after we calculate that antiderivative, we do not need to write the plus c, and then my bounds move to the other side. And so I'm going to take this and evaluate this. And what this will become, the first thing I'll do is I'll take my b value and plug it in. So this is b squared over 2 minus, and then I'll take my 0 value and plug it in, 0 squared over 2. Now if I were to simplify that second term is just 0, so we end up with 1/2 b squared, or b squared over 2. That represents the area. Okay? So if I used my regular formula, because this is a right triangle, and we try to find the area of a triangle, we know that area equals 1/2 base times height. And the base width of this triangle is b, so area equals 1/2 b, and my height is also b. So I have area equals 1/2 b squared. And you can see that these are the same value. We did it using a regular formula, and then also kind of using this new notation, okay? So this is how we're going to deal with a indefinite integral. And so what we can say, we've got some basic rules that we use to help us understand this, but eventually we do not rely on these basic rules. We can then state that we know the integral from a to b of x dx, and I'm going to color code this. I'm going to use a and then b. What that is always going to be equal to is b squared over 2, because that was my antiderivative, minus a squared over 2. Okay, so like right now we are remembering that formula, but moving forward we're not going to want to use that formula. If you think about, say, the integral from a to b, again I'll use colors here, from a to b of x squared dx. Well, what is the antiderivative of x squared? That would be x cubed over 3. So if I had x squared and I wanted to solve this, I would say, well, I need to evaluate that from b to a. And my calculation would then be to plug in b cubed over 3 minus a cubed over 3. So I hope you see here what the pattern is that we're going to use for definite integrals for solving to find the value of that area under a curve. And of course, I do need to specify that b is greater than a, and that just means my upper limit of integration is greater than my lower limit of integration. Okay,